Hello, good evening everyone. So we are going to start the lecture. Okay, in the last discussion I think we have discussed the pushover analysis, and we have I think completed the analysis. I have discussed the result, how to process the analysis results, and what are the parameters you have to look for. Whatever the pushover curve, which is the story shear force versus roof displacement curve, those things we have discussed in the last class. So before starting today's topic, let me know if you have any doubt anywhere in that and last class discussion, or any other things, either in the pushover analysis or whatever we have done earlier. Okay, if not, today we'll move to the next topic, which is the time history analysis of RC buildings. There two things we have to know. First, how to select the ground motions. What are the different parameters you have to consider while selecting the ground motions, and then how to apply the ground motions in the buildings to analyze. Okay, so we'll start with the basic. First we'll see how to select the ground motion, then we'll see how you can apply those ground motions in the building. Okay, so before that I want to ask whether these things are discussed in the class or not. Selection of ground motions, what are the different features of ground motions?
Currently going on, sir.
Okay, so you have some idea about the selection of ground motions, right? This is a just general thing. I want to know whether you have idea at this moment or not.
Little bit, sir.
Okay, so I'll go slowly, and whatever things comes, then that I'll try to discuss. Okay, and if you get any doubt anywhere, let me know. Okay, first quickly I will show how to select how to download the ground motions first, then we'll see how to select the ground motions depending on the various parameters. Okay, so there is one website called peer ground motion database. Okay, so there are a lot of other database also where you can download, but let us see this one. Here two buttons are given where you can click. One is this one, NGA West 2 shallow crustal earthquakes in active tectonic regimes, and another one is NGA East Central and Eastern North America. As you can see here, this part is applicable for USA only. So basically we go for this one, which is applied for the worldwide, wherever the peoples other than USA, they can go for this one. Okay, so accordingly you have to click on this button, NGA West 2, click on enter, and here you can register if you already do not have any account there. I think I have already, let me try. Okay, so you can register, nothing, just enter your email ID, that's all. There is no other things to enter there. Okay, now see, first thing what it asks is whether you want to scale your ground motion or not. Okay, so by default it is chosen as no scaling. Let us see what inside there. Here you see peer NGA West 2 spectrum, user defined spectrum, ASC code spectrum. Okay, so basically what it is asking, the ground motion what you want to select, whether that should be matching a particular response spectrum or not. Okay, you know we have our IS code response spectrum IS 1893. Basically this gives us some response spectrum for different soil conditions. Okay, so this is because this response spectrum actually it is the representation of some kind of hazard. Okay, so that much it means that much of possible earthquake is there for a particular region. Okay, so if you put that response spectrum here, so whatever ground motion will be selected, that will try to match to that response spectrum with the expectation that it will match to that hazard level. Okay, or for a particular soil type, for a particular magnitude of earthquakes, for a particular source to site distance, that magnitude, source to site distance, rupture mechanism, those kind of things you have studied little bit in seismology. Okay, so these parameters you have to enter here. Now this is asking whether you want to match this according to any particular response spectrum, or you do not want any matching, just you want to download some raw ground motion data. Okay, so both things you can do. You can select the ground motion without any matching, or you can select by matching a particular response spectrum. Okay, so first we will see how to download without matching, then I will show you how to match also. Okay, so let us select this one only by default and submit. Here you see the parameters what you want to enter. Okay, if you know the earthquake names already, okay, earthquake names, for example recently you heard about the Turkey earthquake. Okay, so like this, if you have any particular names known, then you can enter that one, and the station where that earthquake was recorded, that also you can enter. And this RSN name is the name of I think in this database they have given some name to that each and every earthquake, so that number if you know, that you can enter here. Okay, but if you do not know, you can leave that. Then see fault type, for which kind of faults you want to download the earthquake. If you know already, then you can enter, otherwise you can leave that, or you want to select by default all types of faults. Then magnitude, for what magnitude range you want to download the earthquakes. Let's say I want to download for 4.5 to 8.5. okay, so whatever earthquake is available in this database having the magnitude more than 4.5 and less than 8.5, those will be selected. Okay, then RJB, this is I think shores to site distance something, so this also you can select if you know. Just roughly I am giving, at the moment I do not have any verified data. Okay, so for example I want to download for 5 kilometer to 50 kilometer. Within this source to site distance, whatever earthquake was recorded, those will be selected. Okay, then rupture length, this rupture length, it means the due to earthquake there will be fracture in the plate. Okay, tectonic plate, you know, wherever the earthquakes is occurring, because of the earthquake the fracture occurs. So what is the total length of that fracture, wherever that fracture occurred, the total length. So again minimum and maximum you can enter here. Let's say 2 kilometer to 20 kilometer, something like that. Then VS30, this is the shear wave velocity. Again it is asking minimum and maximum, so let us give from 100 to 1000, let's say. Then duration of earthquake, if you know, this is D5 to D95. It means 5% of the total earthquake duration to the 95% of total earthquake duration. That period range, if you know, that you can enter here. So like this. Then these are the types of earthquake, which type of earthquakes you want. Okay, So those kind of things, whatever available data you have, you can enter here. And if you do not have anything, don't worry, you do not have to put anything. This is not a mandatory things you have to do, but whatever you know you can enter. Okay, then this damping ratio 5% by default it is chosen. Then arithmetic or geometric suite average, this let us keep by default. Okay, then click on this. So you have got some warning message here. See what is written there. Your search yielded too many records to process for a proper selection. The first 100 records in order of RSN were thus chosen. It means there are many records available, but the search cannot show more than 100, so it is showing only the first 100 which is coming. So here you see, for all the 100 ground motions selected, these are showing the response spectrum, and this black continuous line is the mean of all this response spectrum, and this is mean plus sigma, mean minus sigma, and mean plus sigma. Okay, and here are the records you have. Now whichever you want to download, you can click and download. Okay, let us first see now what are the details available here. This is spectral ordinate according to these SRSS rules. Then record sequence is 6, scale factor 1. So scale factor 1 means this is not according to any scale. We did not modify the earthquake. Whatever the original earthquake was there available in the database, that is given. Okay, without any scaling. Then D5 to D75 17.7 second, D5 to 95 24.2 second. This is areas intensity, I am not sure about this, what is that. And this is the name of the earthquake, Imperial Valley 02, occurrence year is 1940, and station is El Centro. Okay, and magnitude is,
some people are waiting.
sorry, if you can admit, do it whenever someone is waiting in the lobby. Okay, I'm not sure whether you can do or not, just do it if you know. Okay, so magnitude 6.95. Then this is the fault type, strike slip fault, and the source to side distance, rupture length you can see, then VS30 you can see, lowest usable frequency, initial search, all these things I think you don't need. Okay, so this is in general I am showing how to search the ground motions and what are the different parameters. Now when you are actually going to download your ground motions, all these things you have to check. Okay, there will be some particular requirements from your side. For example, you need between this and this magnitude, for example 5 to 7. Okay, so when you are going to search, you will get lot of database, then among this you have to check which are the ground motions between 5 to 7. Okay, similarly you'll have some source to side distance range also, so you'll check this range whether it is suiting to you or not. Similarly you'll have some VS30 range also, so you'll check this whether it is suiting your requirement or not. So based on that you will select. Okay, again one more thing is you will see multiple ground motions for a single earthquake. Okay, for example this Imperial Valley earthquake, maybe there will be multiple stations which have recorded this same earthquake. Okay, so if you have the option to ignore you need 20 ground motions, there are hundreds of ground motions in search result. Okay, so we usually try to ignore the ground motions of same earthquake more than one times. Okay, because anyhow it is same ground motion, so there is no need of download, no need of analyzing for two different recording stations. Okay, but if you do not have sufficient number of ground motions available in your search, then you will not have any option, you have to download. But if you have option, then you can skip multiple recording of same ground motions. Okay, for example, this one, what I am talking about is this one. You can see Parkfield ground motions 1966. This is the same ground motions, but recording station is different. Here you see this is what is Cholames Shandon. This is one recording station. This is array number 12 and this is array number 5. Okay, so these are the record of same ground motion. So what you'll do, you'll try to avoid downloading multiple records of same ground motions if you have the option. Okay, so this is one thing. Now let's see what is inside in the ground motion by downloading one. Okay, download search result, meta plus spectra, download time history records, spectra plus traces. Okay, sorry, this is not the ground motion, this is just the details of the ground motions which is available in the search. So 100 ground motions were available, so these are the details of those 100 ground motions. I think the records are getting downloaded here. Just wait few minutes. Okay, so actually all the ground motions got downloaded here, so we'll see one of them. Okay, see, this is Imperial Valley earthquake at 180 degree. Okay, you'll see this 180, 270, 0, 90, something like that. Okay, so it is giving the direction at which direction this earthquake is recorded. Okay, so this direction information is given, and at means acceleration, then dt means displacement, and vt means velocity. Okay, so basically for analysis of your structure you will be going for the acceleration time history. Okay, so this at, then This is horizontal ground motions, and similarly you will have the information about vertical also. So here it is written up, up. Okay, so wherever up is written, that is the vertical ground motion record. Okay, so here you see Pierre NGA strong motion database record, Imperial Valley 02, date is 5/19/1940, El Centro array number 9, where that record was recorded, and the direction is 180 degree. Okay, it is acceleration time series in unit of G. So whatever readings you have, that is in the unit of G. Okay, then NPTS number of points, this basically number of points is 5372, and the time interval is 0.1 second. Okay, so whatever readings you have here, this is recorded at an interval of 0.1 second. Okay, now based on this information, can you tell me what is the total duration of earthquake for this earthquake? Anyone?
Approx 54 seconds, sir.
Yeah, means exactly it's 53.72 second. This is the number of points you have, and this is the time interval duration. So sorry, time interval. So you can multiply these two, you'll get the total duration of earthquake. So it will be 53.72 seconds. Okay, now how to read this ground motion point is horizontally. Okay, not vertically. Sorry, it means this is the first point, then this is second point, third point, fourth point, fifth point, then again sixth, seventh, like that. Okay, like this you have to read. Now this you have to arrange in a series, like in one column you will have the time durations, and in another column these acceleration values. Okay, then you will plot and you will get some kind of time history. Okay, so again by to arrange this one, because this is in row wise, right? So I have to arrange this column wise, it will take some time. So I will show you one more ground motion which is already available with me. There I'll show you how the ground motion time history looks like. Okay, so this is one process data of one of the ground motion. In first column you will have the ground motion time is time uh, in seconds, then you will have acceleration. Okay, whatever you have seen, that same things, just we have processed, we have arranged in a column. Okay, that's all. This is not the same ground motion, another one, just I am seeing same things, so you will understand. Sorry, this is not ground motion, actually it's the response spectrum of that ground motion. Let me find out one ground motion also. So this one. Okay, so this is the time history we have. Alright, so this is the time history, just a representative time history, how it looks like. Similarly, you'll have each and every time history will looks different, but if you do not observe closely, you will see something similar. Like this, first it is ordinate will be small, then it will slowly increase, then it will start decreasing, then it will go on like this. Okay, so this kind of things. Okay. And you have seen the what is the characteristics of ground motion. Okay, you have the duration, then you have amplitudes, then you have uh, magnitude, duration, then some other parameter features also, typical features of ground motion, this you have studied. Okay, so from this ground motion you can check all these things. Okay, what is the predominant period and what is the amplitude of that ground motion, all these things. Okay, so this is about the selection of ground motion. Now I'll quickly show you how to match the ground motion to a particular response spectrum. Okay, so this is the actually code response spectrum. I wanted to just copy this one, that's why I opened this file. Okay, let me first copy this. And this is MC IS1893 MCE for I think soil type rock site. Okay, this I will keep in desktop. Now let us go back. Here I will select this user defined spectrum. Okay, upload, choose file, go to desktop, and IS1893. Okay, I think we have to give this in CSV file. That's why it's not taking. Yeah. So here you can see this is the target response spectrum we have provided. Now when you search the record, this database will search the record which is matching this this response spectrum. Okay, let's click that. And again, these parameters, whatever you know, you can select here, and if you do not know, you skip that. Okay, so again it is showing there are more than 100 records, so it will show only first 100 records. And here you see some okay. So one more thing is you can go for this one also. uh, these things what you can see here, this is without any scaling. Okay, means original ground motion it is showing. And you can also scale according to particular period. For example, if you want to select the ground motions corresponding to the fundamental period scaling, okay, means the first mode period. Okay, so corresponding to that period, if you want to scale, you can give your fundamental structural period here. Or if you want to select this, if you want to match between a particular range of periods. For example, I want to match my ground motion from 0.1 to 1 second. Okay, so you can give this range here, range of periods. Okay, and this weight is I am not sure, I think how much matching proportion you want, 100% matching or something like that. I'm not sure about this one, what weight it is asking. Okay, So these things you can explore. So this is the way you can also select the ground motion by matching a particular period. Okay, now here you see whether it is matching properly or not. This is our target response spectrum, but the chosen ground motion is showing the mean response spectrum here. It means although we have given the target response spectrum and we asked the software to give the ground motions which is matching, but still you can see this much difference it is showing. Okay, because I think one of the reason is we did not give any particular these things here. Okay, maybe we have to give these things also, then you can software can better understand what are the requirement you have, and accordingly it will give the ground motions. Okay, let's try. Why at the moment I do not know what are the parameters. Or leave it. I do not have any verified parameters at the moment. Okay, so this is the way you can select the ground motion according to a particular target response spectrum. Okay, now let's go back to our structure. So this is the time history you have, and once you have the time history you can apply this to structure. Okay, so these things will explain. Let me take one ground motion. This is one of the ground motion record I have, so I will copy this one. So this is the ground motion I have. Okay, let's go back. First I'll define this ground motion. See here, you have to go to function, then time history, and here from the file you have to choose this one from the file, and add new function. Here you browse it. Here already we have some things. So this is the ground motion we have. Let me open also this. So this is total 29.98 second and I think 0.01 second interval. Okay. Open. Sorry, not this file you have to enter. You have to enter actually this file only. So let me copy this one. This is again acceleration. Okay, and here you can see this is the Northridge earthquake. occurred in 1994. This is the time, and this is the recording station, and this I think the direction or something. Acceleration 299 points, and this is the interval. Okay, so let's copy this. See, now if you open this file, okay, so your reading starts from this line, means this is line number 5. So up to 4th line, this informations actually you do not need for this ground motion records. Okay, means software doesn't need this one. Okay, so what it is asking, header lines to skip. How many lines are there which you do not need? So if you observe here, there are total 4 lines. Okay, so these 4 lines I do not need, so I'll mention here 4 lines, and prefix characters per line to skip this. Leave it, I don't know. Number of points per line. So this is actually how many points you have in this is one of the line, how many points you have, 1 point, 2 point, 3 point, 4 point, 5 points. Okay, so you mention this one, you have total 5 points. Okay, now see here it is showing total 60 close to 60 seconds, but you have actually 29.99, means almost 30. This is because of this one. You have the interval of 0.01 seconds. Okay, so now if you mention this one, here you see this is close to 30, means 29.99. It means you have given the correct information of this ground motion, and this is the time history record actually. Okay, now okay, let us see the response spectrum of this ground motion. Here you see, go to view response spectrum, and here you see for different damping ratio it is showing the response spectrums. Okay, let us see one by one. Altogether it is not looking very much interesting. Let us delete some of these lines which you do not need. Okay, if you want, then again you can enter. So this is showing only for 0.05, means 5% damping ratio, and you see this is the response spectrum actually. Okay, okay, and this is the name of the ground motion you have. If you want, you can delete all these things you do not need. Okay, so our ground motion is defined, and go to load case, add new load case, time history, this will be time history. And what kind of time history you want? Linear direct integration, non-linear direct integration, or non-linear model. Okay, so this non-linear model is also called fast non-linear analysis. Okay, FNA, and this is linear direct integration, so it will consider the structure to be linear and within that range only, I think. And non-linear means it will apply full non-linearity, whatever structural non-linearity you can expect in the structure, it will go up to that. Okay, so go to this, then mass source, we have this one, and zero initial condition, no. Here we'll start from this one, gravity non-linear static case. This already have created when we have analyzed for pushover analysis. Okay, so that same I am applying here. Okay, then add here load pattern. This is type acceleration. Whatever ground motion you have chosen, those data are actually acceleration. Okay, and here this is u1, means you are applying in the x direction. Okay, and function, this is the function we have just defined, and there it is, the unit is in terms of G. Okay, but here you have to give in terms of some unit method, like a matrix unit method, or some FPS unit method, something like that. So we are following the matrix unit method, that will be in Newton meter second. Okay, so you have to multiply by 9.81, okay, to convert unit G to the meter per second square. And see here. Okay, before that let us just select this one, P delta plus large displacement, and here number of output time steps. Okay, so here what you can do, our ground motion have 2999 points. Okay, so if you want to get total 2999 points, output time step size should be 0.01. okay, if you apply time step of 0.01 and you run for 2999 seconds, you can complete this entire ground motion. Okay, but suppose I want to get in between that also some output time steps I want. Okay, so I want to double this one. So if you double this time step, how much you will get? 5998. okay, so if you double this one, what will be this output time step size? Can anyone guess? Means in total I want to run for 29.99 seconds of that time history. Okay, so output time steps I have doubled, so what will be the output time step size? It will be reduced to half, right? Then only if you multiply this and this, you will get total 29.99 seconds. Otherwise, suppose I have not changed this time step size. Okay, what will happen if you multiply this one 50, it will become 59.98, but that much time duration we do not have that in that ground motion. Okay, that's why. But suppose instead of this one I have given 0.001. okay, now what will happen, it will become 5.99 seconds, means our analysis will run for 5.99 seconds, then it will stop. After that analysis will not run for the remaining duration of ground motion. Okay, so these things actually do not have to do anything with the duration of ground motion. These are just the steps, number of steps for what you want to run your analysis. Okay, so we'll put this parameter in such a way that the time duration what we need is covered. Okay, so I have doubled this one, that's why I have to use here 0.005 so that I can get the duration what I want. But no need to double this one, whatever you have you can keep this one only. Okay, 2999, and this will be 0.01. Sometimes what happens, you have by default whatever ground motion you have, by default there may be instead of 0.01 you have 0.1 there. What I am talking about is this one. Suppose here instead of 0.01 you have 0.1, it means the information given here is at interval of 0.1 second. So 0.1 is actually too much. Okay, for analysis that 0.1 time interval is very high, that's why you want to reduce this 0.1. So in that case you can adjust this, you can increase the number of steps and accordingly reduce the this time step size. Okay, in that case you need, but in this case we have 0.01 by default, so that is fine. 0.01 is not that much large, you can analyze for this time step. Okay, so this is the thing you have to understand here. Then damping you will define here. You have different kind of damping here to define. Okay, so direct specification, then according to period, and if you know the first mode of the period. Okay, so this will know once you analyze the structure. For model analysis you will come to know the first period. Okay, so you will put the first period, then you will put the second period of what you want to consider. Let me show this step by running the analysis. So these things I do not need. I want to run for only this one. I want to know the time period of my structure, so model analysis I will run. Okay, okay, so here you see your first period is 1.792 second, but it is in y direction. As you can see, the contribution mass participation is in y direction, not in x direction, so you cannot consider this as first period for your x direction. Here what we are doing, the ground motion what we have applied now, that was for x direction. Let me show once again. See, here I have given this u1, means it is for x direction, so you have to consider the period of that x direction only, not y direction. Okay, and see second one, you see this is in x direction, so this will become the period of x direction, first mode period of x direction, not this one. Okay, so this is 80.94% of contribution. Okay, so let us consider this one, 1.723 first period, and there if you have seen, when I opened the time history page, there it was asking for 2 period. Okay, second period, there are actually number of periods you have, but which period you can consider as the second period. Okay, so basically in normal case we consider the period corresponding to 90, more than 90% of contribution. Okay, so if you look at here, it is 80.94, then if you add, this is also in x direction, so this will be the second period of x direction, but if you add these two, 80.94 and this is 9.96. Okay, so let me see how much I am getting. 80.94 plus 9.96, so it is 90.9, means I can go for this period. Okay, or else if I want to still increase by little bit, then next x period is this one. Okay, if you see here, so if you add this also, this is again 3.18, so I am getting in total 94%. So I can consider either this period or this period. Okay, both are satisfying my 90% criteria. Okay, so let me choose this one only, fifth period, which is the second mode period of x direction, and this is the first mode period of x direction. So this period is 1.723 seconds and this period is 0.558 seconds. Okay, so this is 1.732 I guess, and damping will consider means 5% corresponding to that period, and also this is 0.558 I think, and here also 0.05. Okay, this is actually you have studied in your theory of vibration. mass and stiffness proportionate damping. Okay, so if you have not remembered, go back once again and study that I think chapter 13 there in your theory of vibration Akechupra book, chapter 13 or somewhere close to that. There you'll see one topic, this one, mass and stiffness proportionate damping. This is basically that damping here. Okay, so we define the damping corresponding to two particular periods, then in between any period range it calculates based on a formula given in that. Okay, so you can either put a period here or you can manually calculate also. Okay, if you select this one, it is asking mass proportionate coefficient and stiffness proportionate coefficient, so you can manually calculate and you can put here, or else you can select this one, and as we have done here, you can just choose the period here and give the damping how much you want. Okay, then select OK. Then this is the integration scheme, which integration scheme you want to follow. There are 5 integration scheme you can see. This is numeric method, Wilson method, so, then this is Hibbeler, Hughes, Taylor method. Basically we use this one. I do not have much information about this one. You can search this one and study. Okay, okay, this nonlinear parameters, let us keep by default whatever is there, and okay. So we have defined one time history for our x direction. Okay, similarly you can define another for y direction also, time history. Okay, okay, so here actually do not have any time history defined for y direction, so let us just keep that same time history whatever you have chosen, but it is not like that same time history will apply in both the direction. Okay, so when you are, sorry, one more thing I forgot to explain here. Okay, these ground motions where we have downloaded, here you see this angle 180 degree, 270 degree. Okay, so if you keep this as x direction, then this 270 degree you can keep as y direction. Okay, because this is 90 degree, 180 to 270, so this is 90 degree, right? 90 degree difference, so you can keep x and y direction like that. Either you take this as x direction or this is y direction, or vice versa, you can do like that. Okay, so you'll have different ground motions for x direction and for y directions. Okay, but since here we have not defined two ground motions, so I have just kept same ground motions what I have defined. Okay, and now see here, when we will enter the period, this will be corresponding to y direction, not x direction. Okay, so again you have to see the period corresponding to y directions. Okay, so this is the first period of y direction 1.792, and if you see the contribution, this is 81.53%. The next period corresponding to y direction is this we can ignore, actually this is close to 0 only, do not consider this one, because this is the torsional mode, third mode, which is torsional. Okay, then second y direction period is this one, here you see, so again this is 81.53 and 9.31, so if you add, this will become more than 90%, so you can consider this. Okay, so first period is 1.792 seconds and second period is 0.582 seconds. Alright, so we have defined both the ground motions. Now see, similar to the pushover analysis, in time history analysis also you have to define the hinges, because the non-linearity what you need for time history, or the means the pushover and time history both are dynamic analysis. So in dynamic analysis basically non-linear deformation occurs, so damages will be there, and all these things will be defined, means will be occurring at a region where non-linearity is defined, and non-linearity we define in terms of hinges. Okay, so this definition of hinges what you have learned in the last class during our pushover analysis, same thing will be applied here. Okay, so once again I'll show just briefly, because in details we have talked in the last discussion how to define hinges and how to choose different parameters of hinges. Okay, so in this I'll just show the means I'll just define the hinges. Okay, I will not show in details what are the parameters, how to choose all these things. Okay, so select first beams, select, then assign frame hinges, and auto, let us go for auto hinge, at 5% relative distance, and I see 4130 now we are going for, and this concrete beams, and as we have discussed in the last class, in case of beam we need to consider this M3, moment in third direction. Okay, and here that gravity load case what we have created, that one, and the parameters will be considered from the current design. Okay, so last design data whatever is available it will consider according to that. Okay, I think we do not have any design data available, so let us quickly run a design. So for running design we need to analyze the structure. These things will avoid. Okay, then run. Okay, so I am not going for the discussion of analysis results, directly go for the design, then start design. So all these things we have already discussed many times, that's why I am not explaining once again. Okay, so your analysis is completed. Now you can define the hinges. Okay, you can unlock the model, then go to select, object type, beams, go to assign frame hinges. Okay, So actually there was already hinge defined, that's why you can see in the columns also hinges are available. Okay, but as we have defined now, it will replace the previous defined hinges. Okay, and the analysis what you have run and design also, they during that time you should not have any hinges defined here. Okay, so as I was not sure about whether hinges was defined or not, I have just run the analysis, but this is not the approach. Before running analysis and design, means linear elastic design I am talking about, not the dynamic. So you have to remove the hinges should not be there. Okay, now leave it because we are just practicing, so it's fine. Okay, then we are going to define the hinges for columns. Okay, select the columns, then assign frame hinges. See, so these are the hinges which were already defined there, so I can delete these then again, or you can simply click OK. So all the column hinges are deleted. Similarly, if you want to delete beam hinges, you can do like this. Okay, now select columns and assign. So I have not defined any hinges, so let us go for the auto hinges. Auto means do not say it auto, this is not the correct way to say. Okay, so this is just a default with some default parameters already considered by the software. Okay, but it is not the correct way to say auto hinges. Okay, so do not say it. This is columns, and for column you go for this one, PM2 M3, and this 95. Okay, so now we have our model ready for dynamic analysis using time history. And okay, so these things we have already defined. Then go to our analysis. Okay, either you can run both the direction simultaneously or you can run one by one. Okay, so if you run simultaneously, it will take double time, means both the direction will be running one after the other. Or if you want to run individually, then you can select individual at a time. Okay, so what you need this model case, then you need this gravity case, because as you have seen in the time history step, we have defined this as the initial step, this one. Okay, so you need to run this also. Then let us run for the x direction first. Okay, so remaining load case I do not want to run. Then start running your model. And see here, these are the details you want to look for if you are interested. See, total 29 means this many steps are there, 2999, and this many steps are completed. Okay, and it is running fine, there is no null step. Null step means there is some problem with the convergence, so whenever convergence problem is occurring, you will see some null step here. Okay, as you see 5 null steps. Okay, then total number of steps run so far, and this is the time step size at the current time step of analysis, and this is the time step size what we have defined there, and this is the total time duration for which analysis is completed. Out of 29.99, 3.19 or 3.2 second is already completed. Okay, See 3 point something, 3.2 seconds I guess, somewhere here. Okay, so now if you observe here, the analysis is running very slowly actually. Okay, it has accelerated little bit, but it was running slowly few moments ago. So this is because, as you can see here, up to this range, this amplitude was very small. Okay, so it was not having any significant impact, that's why analysis was running so fast. But after reaching this point, suddenly this amplitude increased. Okay, so it is giving lot of non-linearity to the structure, and because of this, analysis pace actually reduced. Okay, so entire this range from this to this, somewhere here. Okay, so this range will be little bit slow. Okay, sometimes what happens in this kind of situations, analysis also gets stopped in between without running because of convergence problem. Okay, so you may face similar issues. So whenever you are facing these issues, there is no actually remedy for that. What you can do is you can alter the integration parameters. Okay, these parameters you can alter. You can increase the sorry, this maximum and minimum of this iteration, this one 10 40, these things you can change. Then this time step you can change, then damping you can little bit alter, and like this. Okay, so this is just iterative process. By changing the parameters, you will see whether it is running for your model or not. Okay, so sometimes happens this one, if the ground motion is providing so much of nonlinearity which your structure is unable to handle in that case. Okay, so by the time this runs, so let me show these nonlinear parameters where you can alter these things if your analysis is not running. But this is not providing any surety that if you do these things, your analysis will run. Okay, so this is just a try if it works for you. Okay, I'll show you once this analysis completes. So it is somewhere here 3.6, somewhere here. Okay, so let us close the analysis because we have to wait, I don't know for how much time. So this is just a practice, so I'll stop this here and we'll see how the result looks like. Okay, हाय सर. सर क्लास ख़त्म करके आता हूँ. Okay, so you can first see the status of your hinges. You can select your time history load case, and then time step here you can enter. I don't know what is the maximum time step available, so you can enter something like that. Okay, and you can the hinge what you have defined there, you have defined these points B, C, D, E points, and I, O, L, S, and CP, those things. Okay, so this you can choose whether you want to see according to this or you want to see according to this. Okay, so let us first see according to this one and apply. This is not in this direction, so I have to alter the view. Now see, so hinges are formed. here, and this is at the end of 3 point, I think 62 or 69. So till that point what you can see is, see this green zone is I think between B and C, sorry, B and D. Here you see D and here it is B. Then D to E it will show in this, this is something I think pink color or something, and then you will have the red color. Okay, now see at this point you do not have any pink or red color, you have only green, means you all the hinges are performing within the B and C of the backbone curve. Okay, and if you see the result of a particular hinge, then you can go to this hinge results, and here you see this is the hinge at column C1, and this is the number of hinge for what hinge you were seeing the result. Okay, and this is the status of your hinge at this moment, and here you see how much moment is generated here, 4.45 kilonewton meter, and hinge state here you see A to B, and means within this range hinge is still performing within this range only, A to B, and the status is it is still below the IO limit. IO means immediate occupancy, then LS life safety, and CP collapse prevention. Okay, so these things we have provided when we have defined the hinges. Okay, so at this point of the analysis, your this hinge, this particular hinge C1H1 is performing within the IO. Okay, it has not yet crossed the IO limit, and similarly you can change your the hinge here. For each member you have two hinges, so you can change like this, and here you can change the number of member, for what member you want to see. Okay, since we have chosen column here, so it will show the hinges for columns. Similarly, if you want to see for the beams, then you choose the beams, and now see for beam 28, then in the model you can look for which is the beam 28, and accordingly again you will have two hinges in that beam. Okay, so the status of this hinge is again here, this is still here, see hinge state is this one, so it is not perfectly visible actually, because we have stopped the analysis, so it has not run beyond that one. So that's why here you see the state of hinge, again it is A to B range, and again it is within IO limit only. Okay, so IO means it is still in the linear elastic zone, not linear elastic actually, means this is the first step what we have defined, immediate occupancy. Okay, so it is still within that limit only, but up to what range it is completed in that limit, it is not clear. Okay, it is not showing here. And what else you can see, so by seeing this one you can understand. Yeah, any
Sir,
question? Hello.
yes, sir.
Yeah.
Sir, in the diagram we are showing able to see that some in some of the beams hinge are formed, and in somewhere hinge are not formed.
Hmm.
And the result we are seeing
Hmm.
is for some particular beam where hinge is formed or not.
Okay, actually here it is, I have to look for this B28. Okay, let me find out this book B28, which is that one, then you'll understand. For example, if I take this beam, I want to take this beam, and I have to go to undeformed shape for that. Okay, so this is B41. Okay, so if you see whether, 1 minute, let's start from this one. This is, I'm checking for this beam, this is also B41. How is that possible? This is also B41.
Sir, its unique name is changing.
Yeah, unique name is changing, but there that unique name is not showing. No, only this number is showing. This one, B42, B43. Let me show. See once again. Inch. Here unique name is not showing, right? Okay, so here you can actually select. This is the story 1 actually, but how can I check other stories? I should be able to check from here, right? For which story you want. Let us first open this. This is ridiculous. Last one we have seen here, beam column both were coming and we could choose whether for beam or for column we need, but now it is not showing. There is some problem, I don't know what problem actually. So you will be able to check from here for which story you are going to see. Now at this moment this is for story 1, okay, and B43. So so for a particular like this you will select here B43, B41. There is some problem with this. I don't know what problem actually. I am not able to change. Okay. Yeah, now question is, suppose you want to check for this beam, okay, and this is one of the hinge. Let's assume this only. Let's assume this hinge only for this beam and this one, okay. So this hinge is formed, and let us assume that this is the status now, okay. So this has come like this, then it is going up in reverse direction, then again at this point we have stopped our analysis, okay. If suppose we haven't stopped, it would have gone like something like this, then it will come back, okay. So it will run like this, okay. Then at the end of the analysis you will see at what point it has stopped, because see here we have defined our IO, LS and CP. Suppose at the end of the analysis you are seeing entire your hysteresis is within this limit only, okay, for this particular beam hinges. So what you will say, this hinge for this beam has not crossed this IO limit, okay. So this will be your observation. But suppose for some other particular for example, let's say this, suppose it has crossed this IO, LS and CP, it has crossed, okay, then we will say this hinge is collapsed, something like that, whatever you are seeing here, okay. And accordingly this point will change. This point what you are seeing now, this will change. It will show somewhere at some other locations depending on the performance of your hinge, okay. Now ask what question you have. Is it cleared or you still have doubt? Okay, let me know if you have doubt. So like this you can check the status of your hinges, how each of these hinges is performed under the earthquakes, and based on this you can actually optimize your structure, or you can verify your design. For example, if at some particular locations your beam is showing extreme uh, means damages in terms of hinge failure, so what you can do, you can alter your design at that particular location. Maybe you can increase the reinforcement in that particular beam, or maybe you can increase the section of that beam. Then you can alter and you can re-verify, you can analyze again to see whether this performance is improved or not. Okay, so the purpose of seeing the hinge result is this one, just to improve your design. Okay, so like this you can do.
So this deflected shape is for which mode?
This is not for a particular mode actually, so this is not modal analysis. Okay, so this is actually let me show. See time history at this 3.69 time step. Okay, so when earthquake is vibrating the structure, means uh, the structure is affected by the earthquake. Okay, so at this time step, because of the acceleration what is provided by the earthquake, the structure is vibrating in this particular way. Okay, this is not corresponding to any particular mode, but this observation means it looks like something like modal shape only. Okay, it may be it will corresponding to some particular mode, but we are not going to compare this to a modal shape. Okay, it may or may not reflect a particular mode shape, but that is not our purpose to compare that. Okay, so this is happening at this term step, because of the acceleration of the ground motion it is deflecting like that only. Okay, now see, if you change this to some other time step, it will change. Okay, so if you want to run the animation, see, so like this structure is vibrating. Okay, it may or may not reflect some mode shape, but there is no comparison. Okay, similarly this is for one of the frame, then you change your elevation, this is for another frame, then change your elevation like this. So this is for another direction, we have not run for that direction, that's why in this direction you will not see any hinge formation. Okay, so if you run for entire earthquake duration, 30 seconds entire duration, you will see lot of these hinges has failed. In red color or pink color you will see lot of hinges. Okay, so that means those hinges failed in the earthquake, or it need not be, maybe sometimes because of the earthquake is so small that it will not impact, it will not affect severely to the structure, or structure is very much strong compared to the earthquake, so there may be all the hinges will still behave like within IO or within the initial range only. Okay, it may happen, but in most of the cases if strong earthquake strikes the structure, that time lot of these hinges will fail. Okay, so if you run completely you will see these observations. Okay, so like this you can run for the time history, and you can observe the results.
Sir,
Yes,
can we find in this when the first hinge is formed and what is the location of first hinge?
yes, you can find.
How it can be find out?
One way is to go by this observation starting from first time step, sorry, not first time step, let's start from 0. One way is to go by this way, just increasing. I don't know when we will get. Okay, let's increase here only. So this is 0.83. Let us go to 1 second and see. Apply. So still hinges are not there. Let's go to 1.5 seconds. Apply. Still not there. Let's go to 2. Apply, not there. 2.5, apply 3, apply. Yeah, so here you can see one of the hinge, and you can go back one by. Okay, so that was the step where hinge is formed here. Okay, so at this step, so this is one way. Another way is you go to your result, where you can see the result, story response plot. You are not attending
Oh, sorry, sir.
today, class is there, you are not attending.
Sir, I had attended. I had just logged out in between.
Okay, okay, nice.
Thanks.
No, I think in this case that is not possible. That was possible in case of pushover analysis. So in this case, this is the way you will see. Okay, by changing the time step. Okay, so at this time step, then you can display your hinge result, and again for different hinges you can look here for which hinge you want to see the result. In case of beam, you have to first identify the number of this hinge, then you will select here this beam number. First you will identify the beam number for this, then you will enter here that beam number, and again in each beam you will have two hinge, so you have to identify this hinge number and you will enter this number here, then you will see what is the status here. Okay, so this is the way. Yeah, so any more question? Okay, so if not, one more small things I want to discuss. Whatever analysis we have run, that is for natural ground motions, unscaled ground motion. We have not modified the ground motion. Means the original earthquake, what is occurred, that original earthquake we have applied to our structure. We did not modify anything. But when you are designing the structure, our code recommends you match the ground motion to the response spectrum, then you apply to the structure. Okay, so this I will show how to match the ground motion to a particular response spectrum. Okay, you go to modify show function, then sorry, here you have to choose this one, match to response spectrum, then add new function, and there are two kind of matching available. One is spectral matching in frequency domain, and another one is spectral matching in time domain. Okay, so whichever you feel interested you can choose. Let's select this one, time domain. Then target response spectrum you have to choose. Okay, so this is response spectrum 1893 we have. Then reference acceleration time history, this one, this is the one what we have chosen. Okay, then the unit response spectrum unit is in G, and our time history unit is also in G. Okay, then set matching parameter, and match time history, click on that match time history. So this is matching the time history. Okay, now you see this. See, this blue line is showing your original response spectrum, I think, original response spectrum of your ground motion, and this some brown color zigzag line you can see. This is exactly above this target response spectrum, so both are coinciding actually. That's why you may not be able to differentiate this one, but it is exactly matching this target response spectrum. Okay, now see the modified time history. The blue line is showing the original time history, and this again brown line is showing the modified time history. The software has modified this ground motion in such a way that the response spectrum of this modified time history is matching the target response spectrum. Okay, it has preserved some of the characteristics of the ground motion, and according to that one it has modified and given the target response spectrum, given the response spectrum which is matching our target response spectrum. Okay, so okay, and this is the name of the,
Sir,
yeah,
why it is need to be done?
this is because, okay, first let me save, after that I will discuss this. Okay, okay, so this is the modified this ground motion. Now when you are going to analyze the structure for this one, so what you will do, you will just go to this load case, and here you will select this instead of this one, this one. So this is your matched response, matched time history. Now see the question, why we need this to be done. This is because, see, the ground motion what we have chosen, this may not be reflecting the site where you are actually constructing your building. Okay, for example, you want to construct a building at some site in Roorkee. Okay, now if you really want to do some ground motion analysis, you have to select the ground motion which is reflecting the site characteristics of Roorkee. Okay, but there is a higher possibility that you will not get ground motions which is exactly matching the characteristics of that site. Okay, so we have to go for some ground motions from some other site which is not matching exactly to this site. Okay, so now if you select those ground motions, and if you are if you are analyzing the structure without any matching for those ground motions, it will not be a fair uh, what to say, it will not be fair to observe anything from that analysis, because that ground motion may not be reflecting to your site, right? So that's why code says you first match the ground motion to a target spectrum. The target spectrum is our code spectrum, and code spectrum is actually reflecting the hazard for a particular site. Okay, not for a particular site, for a particular zone. For example, you are analyzing for zone 4, Roorkee is coming for zone 4. So in this way it is reflecting the site characteristics of zone 4. Okay, so if you match to that target spectrum, maybe in some way that ground motion will be reflecting your site characteristics, because it is matching the response spectrum of zone 4, right? So now that modified ground motion will be somewhat reflecting to the characteristics of your considered site. Okay, so this is the reason code says to match to the target response spectrum. But suppose you have the ground motion which is matching or reflecting the characteristics of your site. In that case you do not have to go for that site matching. Okay, response spectrum matching. You can analyze the structure for the natural ground motion what you have downloaded, and before doing that you have to show that this ground motion is actually reflecting the site characteristics, then only you can do that. Okay, so this is the fact actually. Yeah, is it clear?
Yes, sir.
Okay, so any more doubt? Okay, so if not, we'll close here, and now you can practice for ground time history analysis, and I think we'll not have any further classes until you have any particular issues, because whatever I wanted to cover I have covered. Now you can practice, and wherever you are getting doubts we'll discuss accordingly, and if you do not have any more issues, we'll I think there is no need to continue further classes for the software. Okay. So we'll close it. So before closing, let me switch off the video.